Chapter 5, Section 5, Bases other than e and applications. As I mentioned, exponential functions have many applications. We're going to get to some of those in this section. But we're also going to consider what happens when we're dealing with exponential functions or logarithmic functions for that matter that have a base other than e. So we're going to do a little pre-calculus as well, and that's what we're starting off with a definition. Now remember that logarithmic natural log functions that are base e, logarithmic functions, the base has to be greater than 0 and it can't be equal to 1. For example, base 10 logarithms we normally call common logarithms. But let's get to exponential functions first. Definition of an exponential function to base b. If b is a positive real number not equal to 1 and x is an element of the real numbers, then the exponential function to base b denoted by b to the x and is defined by b to the x equals, notice how it's defined in terms of the natural exponential function. It's e to the natural log of b times x, and of course if b is equal to 1 you have a constant function, you just have y equals 1. So all the properties apply here for exponents, and let's try an example of an application from our pre-calculus days. It says here that the half-life of carbon-14 is stated to be approximately 5,730 years. I believe in the textbook, if you come across an application problem where they're asking about a different type of radioactive material, they have a list of them in the book somewhere. I can't remember exactly where, but it's in section 5.5, so you can narrow it down that way as well. But the half-life of carbon-14, C14, is 5730. If 100 grams of carbon-14 is present in a sample, how much will be in the sample in 10,000 years? Well, 10,000 years is practically 2 half-lives because the half-life is just over 5,000 years. So you got to figure if you start with 100, one half-life of 5,730 years, you'd be down to 50, and then another half-life, you'd be down to 25. And so since it's not quite 2 half-lives, I got to think it's a little bit more than 25 grams, probably in the 30s somewhere. We'll see what happens here, but we'll go ahead and we'll use a formula that we had in pre-calculus. N equals n sub 0, the original amount, b to the t over k power, where t is the time and k is the amount of time it takes, in this case, for the half-life. B, our base, since we're doing a half-life, is going to be 1/2, and I'm going to have n equals, I'm starting with 100 grams of 1/2 to the t over 5,730. Now it's going to be, from this formula here, we're going to develop a slightly different formula in just a little bit, but for right now, for this example, this is more than enough for what we need. So we're going to try to figure it out for 1,000 years. So n is equal to 100 times 1/2 to the 10,000 divided by 5,730. So it's time to get Mr. Calculator out. What did I do with my calculator? Ah, here it is. Let me clear out what I had from before. So 100 times 0.5 raised to the 10,000 divided by 5730 power. And we get, and I was guessing maybe low 30s, oh, high 20s, almost 30. We get, now it doesn't say where to round to, so we'll say that this is approximately, or excuse me, hang on. Yeah, this is approximately, what do we have, 29.829, and this of course would be in grams. So after 10,000 years, there will be approximately 29.829 grams left of the original sample. Okay, no calculus here, just using the exponential function and a formula that we had back in our pre-calculus days. Now, we define the exponential function using the natural, for base b, using the natural exponential function right here. We're going to now define the logarithmic function to base b using the natural log. So if b is a positive real number not equal to 1 and x is any positive real number, and the logarithmic function to base b is denoted by log base b of x, and it's defined to be log base b of x equal to 1 over the natural log of b times the natural log of x. Now this guy here, you should see this and say, oh, that's the change of base formula, and that's exactly what it is. You should remember this from your pre-calculus days. Some more properties here of base b logarithms. Log base b, that's for any base, not equal to 1, positive number. 1 is equal to 0. The log base b of product is equal to the sum of the logs. Log base b of a quotient is equal to the quotient of the logs. And of course the one with the exponent, where we bring that out in front. All right. Couple more things, because they're inverse functions of one another. The log base b of x and b to the x are inverse functions. We know that y equals b to the x if and only if x is equal to the log base b of y. Also, we know that the base b raised to the log base b of x power is equal to x, as well as the log base b of b to the x is equal to x. These are from the inverse properties, how we get the identity. So we can use those, again, still doing pre-calculus right now, still reviewing pre-calculus. We can do that to solve equations that look like this. Now the first two are exponential equations. The last one here is a logarithmic equation, as you can see. So on the exponential equations, we like to try to match bases if we can, because it's easier to solve that way. I can do that on the first example, but I can't do it on here, because I can write 1 over 125 as 5 to the negative 3 power. 1 over 5 to the third, 1 over 125. So if the bases match, the exponents must be equal. So that tells me that x is equal to negative 3. I can't do that here because I can't raise 10. I can't rewrite 10 as 3 to a power. So what I'm going to do is I'm going to take the log of both sides. Now you can take any log that you want, but since it is a base 3 exponential expression, if I take the log base 3 of 3 to the x equals the log base 3 of 10, I'm just going to get x here from this property, and I'm going to get x equals the log base 3 of 10. Now if they ask for you to rewrite this as a decimal, because you can't really just substitute this into your calculator conveniently, you would have to use the change of base formula here, and that would tell me that this, and I can use common logs or natural logs because they're on my calculator, this would be the natural log of 10 over the natural log of 3, and I can find out what this is on my calculator. Now in this problem here, I'm going to use the fact that if I have it in logarithmic form, I can rewrite this into equivalent exponential form, because there's only a single log here, and this 3 just comes over and kind of bumps this negative 2 right out of the way. Drop the log, I get x equals 3 to the negative 2, I get x is equal to 1/9. So that was kind of convenient to solve. Now let's bring into the calculus the following theorem. Derivatives for bases, and this is for exponentials and logarithmic functions, for bases other than logarithm for bases other than, good lord, other than e, okay, b being not equal to e. Let b be a positive real number not equal to 1, and let u be a differentiable function of x. Now as it turns out, this also works for base e, but it's more convenient if you use the formulas that we had in the previous sections. The derivative with respect to x of b raised to the x is equal to b to the x times the natural log of b. So there's just that extra factor here. Now if this was e to the x, we would get e to the x times the natural log of e, which is 1. So that would just drop out, and I would just have e to the x. So as I mentioned, even though it says other than e, this works for e as well. The derivative with respect to x of b raised to the u, where u is a differentiable function of x. Okay, notice 3 things that we have here, 3 factors. It's the natural log of b times b to the u times chain rule, the derivative of u with respect to x. Now for logarithms, remember that when we took the derivative of the natural log of x, we got 1 over x. Well, we kind of get that here, but the derivative with respect to x for log base b of x, we have that 1 over x part, but we also have that extra factor. Here was up top, but here it's in the denominator, the natural log of b. And then for the chain rule here, it starts out the same way. It's 1 over the natural log of b times u in the denominator, but then times u dx, the chain rule. Okay, the extra constant is why we don't normally go this route, we normally take base e whenever possible. So let's differentiate. Y prime is equal to, now based on this, it'd be this formula right here. This is equal to 5 to the x times the natural log of 5. And you could leave it like that, or you could write the natural log of 5 first times 5 to the x. This one is very similar. It's just that now my function, my exponent is not x, it's a function of x. So I'm going to have that extra step, that extra factor using the chain rule. So y prime equals 7 to the 4x power, all right, that's the b to the u, times the natural log of 7, that's the natural log of b, times the derivative of the exponent. The derivative of the exponent is 4x, is 4. So I can leave it like that. Probably be better off writing this as 4 natural log of 7 in parentheses 7 to the 4x power. And it looks a little bit nicer. Or you can bring the 4 up here as an exponent if you want to, using your properties of logarithms. A couple here. Here's one with a logarithm. And this is going to be more like number 4 here, because what I'm taking the logarithm of is a function of x. And since there's no base written down here, remember it's assumed that this is a common log or a base 10 log. So y prime is equal to 1 over the natural log of the base times the u, which is the sine of x. So I have in parentheses the natural log of 10 times the sine of x times the derivative of u with respect to x. So the derivative of the sine of x is the cosine of x. Now I wouldn't leave it like that. I could write this as the cosine of x all over the natural log of 10 times the sine of x. Now, but notice here, cosine of x and the sine of x, that's cotangent. So I could write this as the cotangent of x all over the natural log of 10. Hopefully you can see that okay. Now here's another one that involves property 2 here, or formula 2 here. Y prime would be equal to 3 to the square root of x times the natural log of 3 times the derivative of the square root of x, which of course is x to the 1/2, so that would be 1/2 x to the negative 1/2. So that would be equal to, I would probably write this as the natural log of 3 times 3 to the square root of x all over 2 the square root of x. And even though there's a radical in the denominator, I think that that's fine. Okay, now those are the derivatives. Let's look at some integrals that involve exponentials with base other than e. Integration formulas for exponential functions, base b, so b not necessarily e, although it works for e as well. Let u be a differentiable function of x. The integral of b to the x dx is 1 over the natural log of b times b to the x plus a constant. Remember how the integral of e to the x was e to the x? Well, it's kind of the same. It just has that extra factor. And the integral of b to the u du is 1 over the natural log of b times b to the u plus my constant there. Just have to make sure that your du is all set up. So we'll try one of each. This one here and this one here. This is going to be, this is your b is 3 here, so this is going to be 1 over the natural log of 3 times 3 to the x plus a constant. Or 3 to the x over the natural log of 3 plus a constant. It looks a little nicer. In this case, my u is 3x squared, so my du is 6x dx. Remember, you have to have your du set up. I've got most of it. I got the x and I have the dx. I just don't have the 6. So I'm going to bring the 7 out in front. And then I'm going to adjust my constant if I have my either one of my pencils here. There it is. So I need a 6 there. So 1/6 on the outside would give me 7/6. So this is going to be 7/6 times, I'm integrating b to the u du, so times 1 over the natural log of 3 times 3 to the 3x squared plus a constant. Now, again, I probably wouldn't leave it in that form. I'd have to be careful here. 7 times 3 to the 3x squared all over 6 natural log of 3 plus a constant. And I don't have to tell you all the different things that could happen. if you check your answer in the back of the book with a problem like this, because they could take this 6 and bring it up as an exponent, all sorts of stuff they could do. All right, now, because of logarithmic differentiation, we can expand the power rule that we had at one time was limited to just rational numbers here. We can allow it to be irrational numbers as well. Any real number, let n be any real number, let u be a differentiable function of x. The derivative with respect to x of x to the n is nx to the n minus 1. And the derivative with respect to x of u to the n is nu to the n minus 1 times du dx. So it doesn't matter even if we have an irrational exponent. Now I have 3 problems that are very similar looking. I just kind of rewrote a couple of things here, and this one kind of finishes it. But what is the derivative of e to the e? Well, there's no variable. E to the e is a constant. The derivative of e to the e is 0, because the derivative constant is 0. What's the derivative of e to the x? Well, we know that one. The derivative of e to the x is e to the x. Okay? And the derivative of x to the e, well, here's my power rule. Because I have an exponent that's irrational, that's okay. This is going to be e times x to the e minus 1. Just that simple. Times, of course, the derivative of x, which is 1, so we really don't even have to apply the chain rule. Now, this guy here is a little trickier. Because the variable is in the base and in the exponent, and you can find the derivative, you'd probably have to use logarithmic differentiation. So if I took the natural log of both sides, brought my exponent out in front, I would have the natural log of y equals x to the natural log of x. Then I take the derivative with respect to x. This would be 1 over y times dy dx is equal to, product rule here, the first one times the derivative of the second plus the second one times the derivative of the first. So I'd have 1 over y dy dx is equal to 1 plus the natural log of x, because this is 1 here. And then I multiply both sides by y, and I have dy dx is equal to the quantity 1 plus the natural log of x times y, which remember was x to the x. So there's my derivative. So that's about all you can do with e's and x's like that. I want to show you the similar problems, how they worked a little different, and similar working problems. That gets me over here to some of the applications. Now, one of the applications, besides, of course, half-lives, would have to do with interest. You guys learned simple interest. Interest equals principal times rate times time. Oh my goodness, probably in middle school. Not even maybe before that. Compound interest we talked a little bit about in pre-calculus, and I'm sure you saw it in Algebra 2. The formula for compounding money n times a year is that the amount is equal to the principal, the original principal, times the quantity 1 plus the rate of interest as a decimal, r over n being the number of times it's compounded a year, raised to the nt power, where n is the number of times it's compounded and t is the number of years. So we could use a formula like this to solve a problem like this. Again, this is pre-calculus here. How much money will one have if $1,000 is invested at 8% compounded quarterly for 2 years? Well, the amount that I would have, $1,000, would be the principal times the quantity 1 plus its 8%, so that's 0.08, divided by compounded quarterly, that means n is 4, raised to the 4 times 2 power. So I have 1,000. 0.08 divided by 4 is 0.02, so 1.02 raised to the 8th power. So now I just grab my calculator. Thank heavens for this calculator at times. 1.02 raised to the 8th power times $1,000 is going to give me 1,171 points. Since it's money, I'm going to round to the nearest penny. It's 659. So 66 here, although the bank probably won't give you credit for that extra fraction of a penny. And so there will be $1,171.61 in the account. All right, now, again, here's the cool part. This part right here, you have to be careful. I have a factor of t here, and then I have an r here. But we know that the limit as x goes to infinity, this is how we defined e originally, of the quantity 1 plus 1 over x to the x power is equal to e. So we take the compound formula and we let the number of times it's compounded a year, that's where the n is, here and here, get bigger and bigger and bigger to what we have, what we call continuous compounding, or compounding continuously. The limit as x goes to infinity of p times the quantity 1 plus r over n to the nt power turns out to equal PERT. P times e to the RT. Now you can go through the steps, and it's just some algebra, but this is the one that you're going to want to remember as well, because this is for continuous compounding. So let's go here. Compound interest formulas. Let P be the amount of deposit. Let T be the number of years. Let A be the balance after T years. Let R be the annual interest rate, and N be the number of times number of compoundings per year. Then for N times a year, the one I had just before, this is your pre-calculus, and now we have the one, and I may have showed this in pre-calculus as well, because we did do some stuff with natural exponential functions. A equals P times e to the RT power. So if I have $5,000 in the account and it pays an interest rate of 8%, I want to find the balance in the account after 4 years if the interest is compounded quarterly or continuously. So I will need, since I ran out of space here, I will need a sheet of scratch paper here so that I can do this work. So let's do part A here first. And I did one just like this a minute ago. A is equal to $5,000 times the quantity 1 plus my interest rate is 0.08. It's compounded, let's see, quarterly. So N is 4, and this is going to be for 4 years. So this would be 4 times 4 up here. So 5,000, 1.0, oh, now N is 4 here, put a 4 there, sorry about that. 0.08 divided by 4 is 0.02. That sounds familiar. To the 16th power this time. So 1.02 raised to the 16th power, get the calculator busy here, times $5,000 is $6,863 and to the nearest penny 93 cents. Now, that's with it being compounded 4 times a year. If I go to part B here and compound it continuously, I would hope that you would know that it would be bigger than this. Now, since it's compounded continuously, you might think, well, it's going to be a lot bigger than this. It's not as much as you might guess, but it should be a larger value than here. So now I'm going to use this formula. I like to think of it as PERT, because it reminds me of the word PERT. 5,000. Times e to the RT, so that would be 0.08 times 4. So I have 5,000 e to the 0.32. So I have to find, oh, I don't have the good eyes on. There we go. E to the 0.32 times 5,000. And if I didn't mess it up too bad, I get 6885, and to the nearest penny, 64. So it's a little bit more. It looks like about an extra $22. So they would have earned, would had in their account $6,885.64. So there's more applications. They really didn't take a derivative here, but there are going to be some problems that involve this upcoming soon. In sections 6 and 7 when we do some work with some differential equations. So be sure to look these over, memorize all these formulas, and practice, practice, practice.